Hello everyone, welcome back to your favorite and India's most affordable learning platform, Physics Wallah. So in the last session of thermal properties of matter, so where we discussed the heat transfer concept and the heat current, so they are part of the conduction, right? So now today the lecture number 5, so where we are going to focus on the thermal resistance and series parallel combination of rods. So how you have studied the series and parallel connection of the resistors in grade 10th. So in the similar way, if the two conductors are arranged in series connection and parallel connection, how the heat current flows in that. So there the electrical current in the electricity, here the heat current. Okay, chalo. So what is the equivalent resistance formula here? The equivalent conductivity formula, all those things we are going to see. Here there we call the electrical resistance, here it is thermal resistance. Okay, chalo. So let's get into the topic, guys. So before that, so as usual, I just need your attention for the next 1 hour, guys. Just be with me, avoid all the disturbances around you, and at the end of the lecture it's very important to prepare your own short notes. Chalo. So let's get into the today's topic. So the first one, let's start with a question. So I gave this question as a homework for you in the last session. Hope you guys solved. So let's try again along with me. So what's the question says? The two ends of a metal rod are maintained at temperatures 100 degrees and 110 degrees. So the rate of heat flow in the rod is found to be 4 joule per second. So if the ends of the rod are maintained at temperatures 200 and 210 degrees centigrade, so the rate of heat flow will be, see here, so the two ends of a metal rod, so there is a metal rod, so consider this is a metal rod whose ends are maintained at 100 degrees centigrade and 110 degrees centigrade. Fine, chalo. So the rate of heat flow, so the rate of heat flow, let it be H1 here, so that H1 is given as 4 joule per second. So 4 joule per second. So if the ends are maintained at the temperatures 200 and 210, so let's take so 200 and 210 degrees centigrade. So then what is the heat flow? See here. So they said same metal rod. So if the metal rod is same, so shall we consider the thermal conductivity will be same, K will be same, right? And then so here let it be the heat H1, and here also let it be the heat H2, right? Done. So now, so the temperature difference in the first case, see here, so the delta T1 is equals to, so 100 and 110, which is nothing but 10 degrees centigrade. So in the second case also the delta T is, let it be, so 10 degrees centigrade again. So 200 and 210, the temperature difference between the ends is 10 degrees centigrade. So now we know that the heat current formula, so Ka delta T by L. Yes or no? So here if you observe the same metal rod, right? So K is same for both. So the cross sectional area is not, dimensions are not getting changed. So A is same, L is same. So here K same, L same, L same. So that means, so H is directly proportional to the delta T, I can write, right? H is directly proportional to the delta T. So shall I use the formula H1 by H2 is equals to delta T1 by the delta T2. So now I can write here, so H1 by H2 is equals to, what is delta T1? 10. Delta T2? 10. So from here, so H1 by H2 is equals to 1. So from here H1 is equals to H2, I can write, so which is nothing but H1 they already gave 4 joule per second. So that means as the dimensions of the rod are not changing, we can say the same amount of heat flows in this one as well, because the ends are maintained at the same temperature and the dimensions are same and the metal rod is also same. So same thing. So the answer is 4 joule per second, option 4. Clear, guys? Understood? Chalo. Good. So let's move further. So the next concept, that is the temperature gradient. See, in any metal rod, so the heat current flows whenever there is a temperature difference, right? So what is the steady rate, steady state and variable state we studied in the last session, right? So the steady state is nothing but, so the temperature of each cross section may not be same, but the temperature at a given cross section should be constant, right? So that's what it is assumed to be. The temperature varies linearly with length at steady state. So the temperature at all the cross sections is not equal in the steady state. At a given cross section, the temperature is going to be constant. The temperature does not change with time. So steady state definition, you remember, right? So the steady state is nothing but, so the temperature at a given cross section, temperature at a given cross section constant with time. Constant with time. So it will not change with the time. So that is called the steady state. So now here let's say the temperature 100. So here 80, just the values are for your understanding. That's it. So 100, 80, 60, 40. So like that there is a temperature difference. Here let the temperature be T1 and here let the temperature be T2. So the temperature T1 is greater than temperature T2. So then the heat flow takes place. The heat flows from higher temperature to lower temperature. Yes, so the heat, let it be H here and the same H flows here. Done? Yes. Chalo. So now the thing is how the temperature is varying if I draw the temperature versus length of the curve. So let me use so let's say this is, so the length x is equals to some length L. So then I can write at some temperature, at x is equals to 0. Let's say this is x is equals to 0 point and this is some x is equals to L. So at x is equals to 0, so the temperature is, let's say, some 100 like this. And then next, so some at x is equals to some 1 meter. So the temperature is 80. So then 60. So then 40. So like this, the temperature is changing with the time. The temperature is changing. This is a temperature versus, so the length L. Getting? Chalo. So here, understand carefully, guys. So here the temperature is decreasing with the length of the rod. Yes. Chalo. So the slope of this one. So what is the slope? How do you find the slope? So this is the slope. Yes or no? So the slope is always measured with respect to the positive x-axis. Okay. So this is the slope. So this slope is given as dt by dx. So you can observe that if the lines are slant towards right, so the slope is considered as negative. And if the lines are slant towards left, so the slope is considered as positive. Yes. So here, or else this angle is obtuse angle, the slope is tan theta. So obtuse angle for tan, it's negative. So that's why, so this is going to be minus dt by dx, minus dt by dx. What is this x? This is the length here. Okay. So I can write, so this is called the temperature gradient. This temperature gradient will be negative actually. This is a temperature gradient which is negative. Done? Clear? Chalo. Everyone done with this? Chalo. So now let me write, understand the concept, guys. First understand the concept, then you can go for the questions. See, we know the heat current formula. So what's the heat current? So or else, so Q, let's write Q first. So the heat transfer, so which is equals to Ka delta T by L into T. Did you guys remember this? Yes. So now, so let's consider this is a metal rod. So I am taking, so the very small cross sectional area. So let's say this is the very small cross sectional area where, So the length of this be let it be dx. So let the length of that be dx. And so the small temperature change here, the dt. So then I can write, so here q is equals to, so q ka, so this is dt by, so the small length dx into t. So in the small time dt, so the very small time dt, so the very small heat flows, that is dq. In the small given cross sectional area whose length is dx, whose temperature change across this cross section is dt. So in this very small time dt is a time. Okay, so the small current flows, that is dq. So not current, the small heat flows, that is dq. From here, so I can write, see, so I can write here, so let's write dq by dt is equals to ka into dt by dx, right? Chal. So what is this dq by dt? Is nothing but the rate of heat transfer, the rate of heat transfer, which is heat current, so which is equals to ka into dt by dx. So this dt by dx is called the temperature gradient. If they mention the temperature gradient in the question, okay, and they asked us to find the heat current, instead of giving the temperature change and the length of the metal rod, so the temperature gradient of this particular metal rod is given this much, and the area of it is given, and thermal conductivity is given, and they asked us to find heat current. So then you can directly use this formula. Okay, clear everyone? And so one more thing here, so generally this h is taken as negative, so this h will be minus ka dt by dx, we write minus ka dt by dx, because this temperature gradient is negative, right? So because this value comes out to be negative, so negative into negative, so it becomes positive. So that's why in textbooks they write this value, the whole formula, as minus ka into dt by dx. Why, sir? Because the dt by dx is already negative, so the negative into negative, the whole heat current will comes out to be positive. Done? Clear everyone? Sure. So understood? So the temperature gradient concept, good. Sure. So let's move further. So let's go for the thermal resistance. See, so before going for the thermal resistance, so let me get back to the basics. So you have studied current electricity in your grade 11th, right? So electricity chapter. In the electricity, see here, so if there is a resistance, now so the current flows in this resistor, so due to what? So why the current flow takes place in any conductor? Here this resistor means it's a load. Okay, so why the current flows in any conductor? When the current flows in any conductor? Whenever there is a potential difference, right? So let's suppose the current is flowing, so then the current flows due to the potential difference, delta V by R, delta V by R. So where this R is a electrical resistance, this R is a electrical resistance, right? Chala. So now, and this delta V is a potential difference, so let me write that also. So the delta V is a potential difference, so I is a current. Chalo. So now let's come to the thermal properties. So where we have a metal conductor, so in this, so the heat current flows, just now we studied in this, the heat current flows. So the heat current flows due to what? Due to the temperature difference. So here the temperature is T1, let's say here the temperature is T2, so the temperature T1 is greater than the temperature T2, then only the heat current flows takes place, right? So what is that heat current? So the heat current H is equals to, so observe carefully, delta Ka delta T, by L, Ka delta T by L. So this is the heat current. This is the heat current. So and then this is the temperature difference. Delta T is the temperature difference. So due to temperature difference, the heat current flows. Here due to the potential difference, the electric current flows. Now, so let me write this as, so due to only temperature difference, the heat current is flowing. So I am writing only delta T in the numerator. So this Ka, shall I write this way? This Ka, L by Ka. Ka, I brought it to down. So then due to here in place of potential difference, we have delta T. In place of resistance, we have this. Okay, so this is the temperature difference and this is a H is equals to now delta T by, so in place of electrical resistance, what do we have here? The thermal resistance. This is called the thermal resistance. H is equals to delta T by RTH. Done, everyone? So this part you should understand. So again, let me write it in the next slide. So we got, so actually the H is equals to Ka delta T by L. So here due to the temperature difference, the heat current flows, right? So I am writing, so the H is equals to, so the delta T, so like potential difference by L by Ka, L by K. So this L by Ka is a thermal resistance. So this L by Ka is called the thermal resistance, right? Understood, everyone? So RTH, the thermal resistance RTH now is equals to L by Ka. The thermal resistance RTH is equals to L by Ka, where L is a, so the length of the given conductor, K is the thermal conductivity, A is the area. So how do you write the units of it? So what are the units of thermal resistance? So don't find units from here, because again writing the K units, A units, L units, so it becomes bit complicated. You can find it, but the easiest way is, so H is equals to, we have got, so delta T by the thermal resistance, right? So from here RTH is equals to, so delta T by H, delta T by H, right? So then you know the delta T units. So what are the units? The units of the thermal resistance. So what are the units of delta T? The Kelvin. And so what are the units of heat current? So what is heat current? So the H is equals to Q by T, right? So the heat flows by time. That is nothing but, so the heat current, so which is nothing but joule per second. So I can write Kelvin second by joule. Understood, everyone? Kelvin second by joule. Done, everyone? Clear, 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 done. So or this one you can also write Kelvin per, so the heat current, it is nothing but watt. Done, clear, everyone? Sure. So very important. So the thermal resistance is nothing but L by Ka. Remember this. Now let's go for, if the conductors are arranged in the series combination and the parallel combination, what will be the equivalent thermal resistance in the series combination of the rods and in the parallel combination of the rods? So let's see the series combination of the rods. See, so we have got, so two rods which are of lengths L1 and L2. So and their temperature difference, see here, so T1 and here theta, here T2. So the temperature, the heat current flows, let's say here the heat H, here the heat H, so here the heat H. So the same heat current flows in the series combination of rods. The first thing is same heat current flows in the series combination of rods. Yes. So in the series combination of resistance, same electrical current flows, right? So you have studied that. So if there are two resistors, this is the one and this is the one. So here if the current is coming, I current, so the same I1 current flows in the second resistor also, because those two are in series, right? Here also the same heat current flows. So obviously you can say that the temperature T1 should be greater than the theta. So then only the heat current flows from here to here. So here T1 is greater than theta, and then so the theta is greater than T2. So then only the heat current flows from here to here and then here to here, right? And then so in this, the theta is called the junction temperature. The theta is called the junction temperature. Just understand the terminology first, so then you can solve the question easily. Done this part? Chal. So now, so what is the heat flow here in the first one? So let me write, so the equivalent of this rod. So let me write, so the equivalent of this rod, that means composite rod combinedly. So what's the composite rod length? So the L1 plus L2. Done. Chal. So this will have the thermal resistance R1. This has, let's say, the thermal resistance R2. So because their lengths and thermal conductivities are different. Chal. And then so let's the R equivalent be the thermal resistance of the composite rod, and the total length will become L1 plus L2, right? Chal. And K equivalent is the equivalent thermal conductivity, we can write. Done. Chal. So now for the first one, let me write the heat current formula. So the heat current H is equals to, for the first part I am writing, so which is equals to, so theta T1 minus theta, so this temperature T1 minus theta, so by, so what's the heat current formula? So the temperature difference by the thermal resistance. What is the thermal resistance? R is equals to L by Ka, right? R is equals to L by Ka. So here the cross section is A, cross sectional area, here the cross sectional area is A, and here also the cross sectional area is A. So theta 1 by theta T1 minus theta by L1 by Ka, L by Ka. So K1, the cross sectional area A. So let the length of the first one be L1. So then the same heat current flows in the second one. So what is that? H is equals to, or else better let's write R1, let's write. So let the thermal resistance of this one is R1. So H is equals to theta T1 minus theta by R1. Let's first get the relation between R1 and R2 and R equivalent. So then we will go for the thermal conductivity. Okay. So then, so this is the heat current in the first rod. So let's find what is the heat current in the second rod. What is the heat current in the second rod? So which is theta minus T2. Here the temperature should be more and here the temperature should be less. So theta minus T2 by, so the thermal resistance of that, let it be R2. So then similarly, so the heat current in the whole composite rod is again same, H. So I can write, so the H is also equals to, let it be the first equation and let it be the second equation number 2, and then H is equals to, so what's the temperature difference here? T1 temperature, here T2, the ends temperature of the composite rod. So I can write T1 minus T2 by, so the whole temperature, the whole thermal resistance R equivalent. So let's write, this is equation number 3. So don't get confused. So we wrote the equation for the first rod, second rod and the composite rod. That's it, the heat current formula. So delta T by R. Done. Sure. So let's add equation 1 and 2. So let's add equation 1 plus 2. So we have got H is equals to, or else let's write this way. Instead of considering these, let's do more simplification. Sure. So what I am doing is, so let's write HR1 is equals to theta 1 T1 minus theta. So let it be equation number 1. So HR2 is equals to T minus theta 2. So then here HR equivalent is equals to T1 minus T2. So now let's consider this is equation number 1. So this is equation number 2. So this is equation number 3. Let me write it in the next page. So here, so we got the HR1 is equals to T1 minus theta, equation number 1, and HR2 is equals to, so theta minus T2, equation number 2, and so HR equivalent is equals to T1 minus T2, equation number 3. Done. Chal. So now let's add equation 1 plus equation 2. So I can write HR1 plus HR2 is equals to, so right side we have got theta T1 minus theta plus theta minus T2. Shall I write like that? So then see here, so I can write, so here theta gets cancelled, HR1 plus HR2 is equals to T1 minus T2. So let's do one more step. So here H I am taking common, R1 plus R2 is equals to, so T1 minus T2. What is T1 minus T2? HR equivalent. HR equivalent. So here H gets cancelled. So then I can write, so the R equivalent is equals to R1 plus R2. So in the series combination of resistor thermal conductors, so we can write the R equivalent, the thermal equivalent resistance is equals to R1 plus R2, same as of the resistors which are connected in series combination. Understood the concept, everyone? Chalo. So let's write, so you can remember now. So the final, the R equivalent is equals to R1 plus R2. So if there are more conductors, R1 plus R2 plus R3 and goes on. So this is a equivalent thermal resistance. Done. So note it down, just have a look at this one, everyone. Hope it is clear. Chalo. So now let's go for the what is equivalent thermal conductivity. Let's find what is equivalent thermal conductivity. So let me add one more slide here. So equivalent thermal conductivity. So when the rods are connected in the series combination. Chalo. So let's do one thing. So again, let me draw the diagram quickly. So this is the rod. So the same cross sectional area A. So and here the junction temperature theta. So here the temperature T1 and here the temperature T2, right? And then here the heat current flows H1, here the H, here H and here H, series combination. So let it has K1 and it has K2 thermal conductivity, and then we have, this is the length L1 and this is the length L2, right? Chalo. So then after combination of these two rods we get the composite rod. So this is a composite rod. So then this is a K equivalent, and then I can write, so the total length will become L1 plus L2. So then the cross sectional area A, so the heat current H, so the heat current H. Here the temperature T1 and here the temperature T2. Yes or no? Chal. So then I can write, so the L1 is equals to, so let the thermal resistance of this one R1, here R2, here RTH. So let me use this formula. So I can write, so the R1 is equals to L by Ka. So the first one L1 by K1A. Let it be the equation number 1. So then R2 is equals to, so let's write, so L2, the length of the second rod is L2 by, so its thermal conductivity is K2 and the cross sectional area A. So let it be equation number 2. Then, so the RTH is equals to, so the total length L1 plus L2 of the composite rod by the total equivalent conductivity Ke, and the cross sectional area is same, right? So and then let it be the equation number 3. So then we know that, so the R equivalent is equals to R1 plus R2 in the series combination of rods, right? Chal. So what is RTH, R equivalent or RTH? This is R equivalent. R equivalent. So the R equivalent is nothing but, so L1 plus L2 by KEA is equals to, so L1 by K1A, L2 by K2A. Done. So A gets cancelled. So then I can write, let me do the calculations here. So I can write L1 plus L2 by KE is equals to, so L1 by K1 plus L2 by K2, right? So what do we need actually? So we need the K equivalent. So let's do one thing. So the K equivalent by L1 plus L2 is equals to, so I can write, let's do one thing better. So write them reverse. So K1 by L1 by K2 by L2. So just we are writing the fractions reverse. So then I can write, so this part if you send it to that side we get into L1 plus L2. So let's do one thing better, write the final formula. So the K equivalent, so let me write this way. So the K equivalent is equals to L1, I'm sending it to this side and sending this whole part to this side, L1 plus L2 by L1 by K1 plus L2 by K2, that's it. So you can use this as a final formula for the equivalent conductivity. So just I sent this whole part to this side and this whole part to this side, so that the K equivalent is equals to L1 plus L2 by L1 by K1 plus L2 by K2. So if there are more rods are connected in series combination, so then you can write L1 plus L2 plus L3 till Ln by L1 by K1 plus L2 by K2 plus L3 by K3 till Ln by Kn. Done? So clear guys, this is a K equivalent and this is a R equivalent. So just let me write the summary. We have got many equations. So let me do one thing. So series combination of rods, summary. Series combination of rods, summary. So let's write this way. So what we have to remember here, sir? So we have to remember what is the thermal conductivity, the thermal resistance first. The RTH is equals to L by Ka. So this is a main formula first you have to remember. And in the series combination of rods, so the R equivalent, the heat flow, so the heat current H1 is equals to H2 is equals to H. If there are two rods, if there are 3 or 4 rods connected, H1 is equals to H2 is equals to H3 is equals to H, like that you can write, right? And then, so the R equivalent will be equals to R1 plus R2. So if two rods are connected in series combination, R1 plus R2. If many are connected, R1 plus R2 plus R3 till Rn, right? So then we have got, so the K equivalent, so which is equals to L1 plus L2 by L1 by K1 plus L2 by K2 plus L3 by K3 and goes on. So this is a K equivalent, the equivalent thermal conductance, so equivalent thermal resistance, so the heat current and the thermal resistance. So these are the things we have to remember in the series combination of resistors, not resistors, conductors. Done? Everyone clear with the calculations? Done guys? Chalo. So just note it down. So we have, see sometimes, so if the two conductors have the same length or the same, if they are having, so the standard result they might ask, so if the two conductors which are in the series combination have the, let's say, same length. If two conductors in series combination have same length, if they have the same length, so that means L1 is equals to L2 is equals to, let's say, L, both have the same lengths. So then what equivalent conductivity will become? So K equivalent is equals to L1 L2, which is nothing but L plus L by, so L by K1 plus thermal conductivities are different, L by K2. So I can write this as 2L by L plus, so L take it common, so 1 by K1 plus 1 by K2, right? So L gets cancelled, so 2 by, so here LCM is K1 K2, so here K1 plus K2 it will be. So then K2 K1 K2 by K1 plus K2. So 2 1 K1 K2 by K1 plus K2. So this is a equivalent conductivity. So if the two rods have the same length, so the standard result. Done guys, everyone? Clear? So just note these things down. Over. Chalo. So let's go for the next concept. So we don't need another slide here. Chalo. So how do you find the junction temperature? See, finding the junction temperature, you know that. So in the series combination, so the same heat current H flows here, and the same heat current H and the same heat current H flows from here. So then I can write here, so the temperature, the heat current here, which is equals to H is equals to T1 minus theta by, so the thermal resistance, let it be R1. So here H is equals to theta minus T2 by, so the thermal resistance R2. So here this is, both are same, their LHS are same, I can equate their RHS. So T1 minus theta by R1 is equals to theta minus T2 by R2. So that's it. So you can find the if you know the temperatures R1 and R2, so you can easily find, temperatures T1 and T2, you can find the theta easily. You know how to find the R1. R1 is nothing but L1 by K1A. So if they are connected in the series, their areas might be equal, might not be equal. You can take area A1, area A2 also. So and R2 is equals to, you know that, L2 by K2 A2. That's it. So just substitute the values. Understood, everyone? Clear? Chal. So we got one question. So let's try this question on your own. If two metallic plates of equal thickness and thermal conductivity is K1 and K2 put together face to face like this. So that means series combination, face to face. Here they mentioned that this is a series combination. So and a common plate is constructed. So that means the composite rod. So then the equivalent thermal conductivity. Equal thickness means what does it mean here? So what does it mean by equal thickness? So their lengths are same in this case. So here, if their lengths are same, L1 is equals to L2 is equals to L. The equal thickness means their lengths are same here. So then I can consider, so the equivalent thermal conductivity, so 2 K1 K2 by K1 plus K2. So the standard result just now I have explained. So 2 K1 K2, where is that? 2 K1 K2 by K1 plus K2. So the standard result. So where is that? Option 2 is the correct one, guys. Done? Direct question. Chal. So let's move further. So we got one more question. See, here the two rods are connected in series combination, but their areas are not same. Okay, so the areas might be equal, might not be equal. So but their lengths are same. Okay, so chala, so try this question on your own, everyone. A metal rod of length 2 meters. So one rod is of 1 meter, another rod is of 1 meter. Has cross-sectional area 2A and A. So their cross-sectional areas are different. Their ends are maintained at temperature 100 degrees centigrade and 70 degrees centigrade. So the temperature difference is given. So the temperature at the C. So whatever the heat current that flows from here, so the same heat current flows in this, because it is a series combination, right? So then how can we write the formula? So 100 minus C, 100, this, let the temperature of this one be, resistance of this one be R1, let the resistance of this one be R2. So 100 minus C by R1 is equals to, so C minus 70 by R2. C minus 70 by R2. Yes or no? So this temperature will be more, this temperature will be less. Then only the heat current flows. So can you find what is R1? R1 is L1 by K1A. Right? So then their K1, K2 values are given in the question. So a metal rod. So a metal rod of length 2 meters. Same rod, K is same. So R2 is equals to L2 by K2A. So then I can write, so L1 is 1 by K1 is K, area A1. So the first one area is 2A, and then so here R2 is equals to length L by K2. So K2, what is K2? K, same metal rod, into area, cross sectional area A. Okay, done. So then, so substitute the values 100 minus C by, so here R1 is nothing but 1 by K into 2A I am writing. Chalo, so here C minus 70 by, what is R2? So L by Ka. L is nothing but 1, right? This is 1 by Ka. Both have the same lengths, L1 and L2. L by Ka, 1 by Ka. So 1 by Ka. So let's do one thing. Send this to upside. K into 2A into, so 100 minus C is equals to K into A into C minus 70. So here Ka gets cancelled. 2 into 100, 200 minus 2C is equals to C minus 70. So send this to that side. So we have got 3C is equals to 270. Then C will be equals to, so 90 degrees. C will be equals to 90 degrees centigrade. Option 3 is the correct answer. Done? Concept clear, everyone? Chala, good. So next what do we have? So the parallel combination. So this part is also easy. You can solve it easily now. So in the parallel, remember this way. So if some current is coming, let me write aside. Just imagine this way. So compare it with the electrical resistors. So let's say some current I1 is coming, some current I is coming here. So then the current will be divided between the parallel resistors. I1 current flows in this and the I2 current flows in this. So again the total I current comes out as I current total. So here the same thing, let's suppose, so some heat current H is coming. So then the H1 heat current flows through this one and H2 heat current flows through this one. Here two metals, they have the thermal conductivity is K1 and K2. Their ends are maintained between the temperatures T1 and T2. Their cross sectional areas might be different or might be same. Okay, so A1 and A2 I am taking. So but their lengths here I have taken same. Okay, let's get the general formula. So write the same equations, right, for the equation 1 for the rod 1, equation 2 for the rod 2, and then finally we get, so the whose cross sectional area will become A1 plus A2, and their ends are maintained at the temperatures T1 plus T2. Sorry, T1, not T1 plus T2. So it's T1 here and it's T2 here. Okay, so the K equivalent will come, and what else? So let the resistance of this one be R1, let the resistance of this be R2. So the R equivalent will come. That's it. So the length remains same. If the length is of L and L, so this is the length, total length L. So can you write the equation same as of the previously we wrote for the series combination, right? So similarly you can write for the H1, H2. See here the heat currents are different. H1 equation, H2 equation you have to write. So what is H1? T1 minus T2 by R1. So H2 T1 minus T2 by R2. That's it. Same first equation you can write. So what is H1? H1 is the temperature differences T1 minus T2 by the thermal resistance of that R1. And then next the H2 is equals to, so what's that? T1 minus T2 again by the R2. And then so the total heat current, let it be H. So the H is equals to, here in this the H flows, in this the H flows. H is coming actually and dividing, and again H is coming out, right? So which is T1 minus T2 by the R equivalent. So now do the calculations. Just add the equations here. So the total heat current must be equals to heat current 1 plus heat current 2. So here it is divided, right? H1 plus H2. So the total heat current H is equals to H1 plus H2. So hope you guys are solving along with me. So T1 minus T2 by R equivalent is equals to, so T1 minus T2 by R1 plus T1 minus T2 by R2. So here either side T1 minus T2, T1 minus T2, T1 minus T2 gets cancelled. So I can write 1 by R equivalent is equals to 1 by R1 plus 1 by R2. So, and goes on. If there are more conductors which are connected in parallel combination, so we can write 1 by R equivalent is equals to 1 by R1 plus 1 by R2 plus 1 by R3, goes on. So in the resistors case also, you know, right? So 1 by R1 plus 1 by R2. So you can also write here, if there are only two conductors which are connected in parallel combination, so the R equivalent, so the general formula that you can write R1 R2 by R1 plus R2. So this also we know, R1 R2 by R1 plus R2. This is a equivalent thermal conductance, equivalent thermal resistance of two rods connected in parallel combination. Connected in parallel combination. Clear, guys? Understood? Everyone? Sure. So this part is also done. Sure. So can you find the equivalent conductivity in this, in the parallel combination? So can you find the equivalent conductivity now? So try that. Find the equivalent conductivity. Simple thing. Same previous one. So the equivalent conductivity in parallel combination. So let me draw the diagram quickly again. So we have got, so two rods. So this is the one, and then so this is one more rod, so which is of length same, and cross sectional area A1, cross sectional area A2. So here the temperature T1 is maintained, and the here temperature T2 is maintained, right? Chalo. So then the composite rod, so that we get whose area will become A1 plus A2, and the heat current that flows in the first one, here it is H1, here the heat current that flows in the second one is H2, and here the H and here the H. So here the equivalent conductivity Ke, so here K1, here K2, so resistance R1, resistance R2, so here the resistance R equivalent, right? Chalo. So first let's write the R1 formula. So what is R1? So the length L by, so the K1A, K1A1, and then so the length L2, so which is equals to, so if you take the lengths also different, so let's say this is L1, this is L2, instead of taking the same, so if you take the lengths are different, so then the whole length will become okay. So let's let the length be L only, better. So L by K1, K2 A2, yes, K2 area A2, yes, good. So then R equivalent will become, so the total length L by K equivalent into A1 plus A2, yes, done. So now you can substitute the values. So 1 by R equivalent is equals to 1 by R1 plus 1 by R2. So here L1, L2 is equals to the length L I am taking. Substitute the values now. Just substituting the values. 1 by R equivalent is equals to 1 by R1 plus 1 by R2. So what is 1 by R equivalent? R equivalent is L by K equivalent into A1 plus A2. So which is equals to 1 by R1. So 1 by L by K1 A1 plus 1 by L by K2 A2. Right? So chalo. So then which is equals to, so this goes up, so Ke into A1 plus A2 by L is equals to K1 A1 by L plus K2A2 by L, right? So L gets cancelled. So the K equivalent is equals to, so K1A1 plus K2A2 by K1A1 by plus K2A2 by A1 plus A2. So the K equivalent in the parallel combination of the conductors which are connected in the parallel combination of the conductors is K1A1 by K2A2 by A1 plus A2. So in the series combination we have already seen. So what is it in the series combination? So L1 plus L2 by L1 by K1 plus L2 by K2. So that's a series combination, and this one is a parallel combination. So the equivalent conductivity we have separate slide, so but not required. So here you can get one more standard result. So what's the standard result? If the two conductors have the same, area, if two conductors in parallel combination, if the two conductors in the parallel combination have same area, then so we can write, so the A1 is equals to A2 is equals to A. So the same area, A1 is equals to A2 is equals to A. So then what's the K equivalent formula in the parallel combination? K1A1 plus K2A2 by A1 plus A2. Done. So K equivalent is equals to K1, so let it be, and first one A, and K2, so the second area is also A, by A1 plus A2, which is A plus A 2A. So the K equivalent is equals to K1 plus K2 into, so the area A by, so the 2A, area cancel. So the K equivalent is equals to, so we can write simply K1 plus K2 by 2. So if their two areas are same, the conductor has same areas, so then you can use this formula. Done guys, everyone? So let me write what you have to remember in the parallel combination of the rods. So in the case of parallel combination of rods, just write as right here, parallel combination of rods. So let's write the summary. So here the heat current in both the rods is not going to be same, it gets divided. Yes or no? So the first important thing, so the heat current is not same. So the total H is equals to H1 plus H2. And coming to, so the resistances, thermal resistances, so 1 by R equivalent is equals to 1 by R1 plus 1 by R2. If there are more, so you can add plus 1 by R3 plus 1 by R4 like that. And then we have got, so K equivalent is equals to K1A1 plus K2A2 by A1 plus A2, right? So if they have the same length, so same area, sorry, A1 is equals to A2 is equals to A, so then the K equivalent will become, so K1 plus K2 by 2, K1 plus K2 by 2. So this is a parallel combination summary, and this is a series combination summary. Where is that? So just write these two again in one page. So I don't want to write, so because again it's a time waste. So I have one slide here, so for summary, and we have one more slide here for the parallel combination summary. So you guys just write them at one place. So to avoid the confusion, so just write them at one place and just have a look at those formulas. Clear? Everyone? Done? Chalo. So we have got one question. So try this question on your own. So two rods A and B of different materials. Different materials means, see here, so their thermal conductivities will be different, are welded together as shown in the figure. So they are not welded face to face, so they are welded one upon the another, overlapping, so which is nothing but, so the parallel combination. I can directly first observe that it has a parallel combination, right? Chalo. So next, so the thermal conductivities are K1 and K2. So the thermal conductivity of the composite rod. So what's a composite rod? So that is, here they did not talk about anything about the area, right? So here the heat current H comes, here the heat current H. So which divides here H1 and here the heat current H2. So the K equivalent, they did not talk about the area, consider the area is same. So if they did not mention, consider the area is same for the both. So if the area is same, so the K equivalent for this will become K1 plus K2 by 2 directly. So direct standard result. So you can choose the option 1. Done guys. Just now we have did the standard result, right? So you can directly put the option. Okay. Done. Sure. So good. So hope you guys can take these questions as a homework. So consider this as homework 1. So this as, I am deleting this, you can solve it on your own. So if you are not getting, I'll take it in the next class. Homework 2. So don't need of this slide. So just first try it on your own guys. Anything if we have given. So 2 slides we have. So once the class is done, you should try it on your own. So then only you'll get. So total how many questions here? So homework 1, homework 2, same concepts. So just try to apply the concept what we discussed. Homework 3 and the homework 4. So these 4 questions are important and previous year questions. So JEE and NEET based questions. So actually, so if you are not getting, I'll solve them in the next class. But you guys should try it on your own first. Chalo guys. So we'll meet in the next session. So with the radiation concept. So till then, keep studying. All the very best. Bye.